a ship as long as 5 football fields, loaded with enough oil to fill 4,500 Olympic swimming pools, weighing more than 600,000 tons. That is heavier than 4 million cars stacked together. Now here is the strange part. That same ship is made almost entirely of steel, and steel is 8 times heavier than water. Drop a steel spoon in a bathtub and watch what happens. It sinks in less than a second. No hesitation, no struggle, straight to the bottom. So how does a steel monster the size of a small city float calmly on top of the ocean, day after day, year after year, without a single problem? This is not a trick. It is not some special kind of magic steel that weighs less than normal steel. The steel in that giant ship is the exact same steel as your spoon. Same weight, same material, same rules of nature, and yet one sinks in a bathtub and the other carries 500,000 tons of cargo across open ocean without even getting close to sinking. For over 2,000 years, this question confused some of the smartest people in the world. Kings wanted bigger ships for battles. Traders wanted bigger ships for goods. But everyone ran into the same wall. Metal sinks. Everyone knew it. Everyone had seen it with their own eyes. So for centuries, ships were built only from wood, because wood floats on its own and nobody needed to understand why. But wood has a huge problem. It rots, it burns, it snaps in bad storms, and there is a hard limit on how big a wooden ship can ever be, because wood is simply not strong enough to hold together at massive sizes. If humans wanted bigger, stronger, longer-lasting ships, they needed metal. But metal sinks. It seemed like an impossible dead end. Then, a small group of stubborn engineers decided to test that belief. What they discovered did not just change ships. It changed how humans move almost everything around the entire planet. By the end of this video, you will understand exactly why a 600,000-ton ship floats while a small coin drops straight to the bottom. You will learn about a wild bet made over 200 years ago that nobody thought could be won. You will see how modern submarines sink and rise on command like it is nothing. And near the end, we are going to answer a question that might surprise you. Is there actually a limit to how big a ship can be? The answer is stranger than you might expect. Before we get into any of that, if you find this kind of thing interesting, hit subscribe now. Here is the real reason to do it. Most videos about science just throw facts at you and move on. This channel is different. Every video we make ends with a twist you probably did not see coming. A fact that makes you stop and go, wait, really? If you like that feeling, you are going to want to be here for what comes next. Because this is only the beginning of the story. Let's rewind about 250 years, to the moment one man risked everything on a bet that seemed completely insane. Section 2. A crazy bet that changed history. In the year 1787 in England, a businessman named John Wilkinson made a bet with his friends. It was not a small, friendly bet either. It was a big one, with serious money on the line. Wilkinson believed something that almost nobody else believed. He believed that a boat made entirely out of iron could float on a river without sinking. His friends thought this was ridiculous. And honestly, who could blame them? At that time, iron and metal were seen as the heaviest, sink-fastest materials known to regular people. If you dropped an iron tool in a lake, it disappeared in an instant. Every blacksmith, every sailor, every regular person had seen proof of this their whole life. So when Wilkinson said he was going to build an iron boat and sail it down the river, his friends laughed and happily took the bet. To them, this was free money. Wilkinson built his boat. It was about 21 meters long, made from iron plates joined together, with a flat bottom like a big iron bathtub shape. The day came to launch it into the Severn River. A crowd gathered. Some people came just to watch what they were sure would be a total disaster. Picture the boat sliding into the water and instantly vanishing under the surface, sinking straight down like a rock. That is not what happened. The iron boat touched the water, settled down a little bit, just like Wilkinson had predicted, and then floated calmly on the surface. It did not sink even a little more than expected. Wilkinson had done the math ahead of time, and his math was correct. His friends had to pay up. Wilkinson earned a funny nickname after that. People called him Iron Mad because building a metal boat seemed like a crazy idea. But he was the one laughing in the end because he was right and everyone else was wrong. Still, a small iron boat floating calmly on a quiet river is one thing. A giant iron ship surviving the open ocean with huge crashing waves and violent storms is a completely different challenge. Many people still doubted that iron ships could ever survive real ocean conditions. A river is calm, the ocean is not. It took almost 60 more years before the world got its answer. In 1843, in the city of Bristol, England, a massive ship called the Great Britain was launched into the water. It was designed by a brilliant engineer named Isambard Kingdom Brunel, and it was unlike anything the world had ever seen. This was the very first iron ship built for regular trips across the Atlantic Ocean, and it even used a spinning propeller instead of old-fashioned paddle wheels. The ship stretched 98 meters long. For the year 1843, that was an unbelievable size. Newspapers at the time predicted total disaster. Many writers confidently said this iron giant would sink to the bottom of the ocean the moment it left the harbor, taking its passengers down with it. Crowds actually gathered at the docks, hoping to witness the shipwreck with their own eyes. That sounds harsh, but that is genuinely what people expected to happen. Instead, the massive iron structure, weighing about 1,000 tons, slowly and smoothly slid out of the harbor and sailed out into open water. It did not sink. It crossed the entire Atlantic Ocean successfully. Later, the Great Britain actually ran aground on rocks near the coast of Ireland. It sat stuck there, exposed to crashing waves, for more than a full year. If this had been a wooden ship in that exact situation, it almost certainly would have been smashed apart by the waves within days. Wood cracks. Wood splits. Wood cannot handle that kind of constant beating. But the Great Britain survived. Engineers eventually pulled it free from the rocks, and the ship went right back into service like nothing major had happened. That single moment changed everything about how ships were built. After that, shipbuilders around the world stopped asking, "Will an iron ship sink?" The question completely flipped. Now everyone wanted to know something different. If iron ships do not sink, how does that actually work? And more importantly, how big can we push this idea? To answer that, we need to go back even further than Wilkinson's bet, all the way back to an idea that is over 2,000 years old. Section 3. The secret nobody could see. For 2,000 years long before iron ships, long before steel ships, there was a Greek thinker named Archimedes. He lived over 2,000 years ago, and according to legend, he figured out the secret to floating while sitting in a bathtub. As the story goes, he noticed that when he lowered his body into a full tub, water spilled out over the edges. That simple observation led him to a rule that still explains every single floating ship on Earth today. Here is the rule, explained the simple way. When you put an object into water, the water pushes back against that object. The water pushes up with a force equal to the weight of the water that got shoved out of the way or displaced by the object. Try this in your head. Push an empty cup down into a pool with the open side facing down, like you are trying to trap air under it. You will feel the water pushing back against your hand, trying to force the cup back up to the surface. That push you feel is the exact same force that holds up massive ships. It is not a mysterious force. It is water fighting to get back into the space that something else is taking up. Now here comes the part that trips people up. Steel is roughly 8 times heavier than water for the same amount of space it takes up. So how in the world does a steel ship not sink instantly, the same way a steel spoon does? The answer is not about what the ship is made of. The answer is entirely about shape. Try a simple experiment in your mind. Take a flat sheet of metal and drop it flat into water. It sinks immediately, no surprise there. Now take that exact same sheet of metal, same size, same weight, and bend it into the shape of a bowl or a cup. Drop that shape into the water instead. This time, it floats. Same metal, same total weight, completely different outcome. Why? It comes down to something called density. But let's skip the fancy word and just think of it as how packed together something is. A flat sheet of metal is almost entirely solid metal, with barely any empty space inside its shape. Because of that, the average packed togetherness of that flat sheet is almost identical to the packed togetherness of solid steel itself, which is way heavier than water, so it sinks. But when you bend that same sheet into a bowl shape, something important happens. Now there is a big pocket of empty space trapped inside that bowl shape, and that space fills up with air. Air is incredibly light, way lighter than water. When you combine the weight of the metal with all of that trapped air and then look at the average packed togetherness of the whole shape together, the number drops dramatically. It becomes lighter, on average, than water. That is why it floats. This is the entire secret behind every steel ship ever built. A ship's hull is not just a solid block of metal. It is a giant, hollow shape, like a massive metal bowl turned right side up, filled mostly with air, along with cargo and empty rooms and hallways and engine spaces. When you average out the weight of all that steel together with all that empty air-filled space, the total package ends up lighter, on average, than the same amount of ocean water. That is the whole trick. That is why a 600,000-ton ship can float right next to a small steel bolt that sinks in 2 seconds. Shipbuilders figured this out a long time ago and used it constantly, long before anyone could fully explain the science behind it with numbers and formulas. But here is where things get even more interesting. Engineers eventually learned they could actually control this floating power on purpose. They found a way to make a ship sink lower into the water or rise higher out of the water whenever they wanted to, just by changing what is stored inside the hull. Here is where it gets interesting, because this next part is used in some of the most incredible machines ever built by humans, including machines designed to disappear underwater completely on command. Section 4. Ships that choose to sink. A modern ship is not just one giant empty room inside a steel shell. Inside the hull, there are dozens, sometimes even hundreds, of separate sealed sections. Each one has its own job. Some hold cargo, some hold fuel for the engines, some hold fresh drinking water for the crew, and some are left almost empty on purpose, filled only with regular seawater, used specifically to control how the ship sits in the water. These special seawater sections are called ballast tanks, and they are one of the smartest tricks in all of ship design. Here is the problem ballast tanks solve. When a big cargo ship is empty, with no cargo loaded inside it, it actually sits very high up out of the water. That might sound like a good thing, floating even higher, right? Actually, it is dangerous. When a ship sits too high, its balance point shifts upward, and even small waves can start rocking it violently side to side. An empty ship riding too high can become unstable and unsafe in choppy water. To fix this, the crew opens valves and lets seawater flood into the ballast tanks on purpose. This makes the ship heavier again and pushes it down lower into the water, which makes it much more stable and steady, even without any cargo on board. Later, when the ship reaches a port and gets loaded up with real cargo, the crew pumps that ballast water back out into the ocean. If they left the ballast water in, while also adding a full load of cargo, the ship would sink way too low, and dangerous waves could start splashing right over the deck. So the crew constantly balances cargo weight against ballast water weight every single trip, and getting those numbers right is a serious part of keeping the ship and crew safe. Submarines take this exact same idea and push it to the extreme. A submarine is basically a ship that can fully control its own floating power at will. When a submarine needs to dive underwater, its crew opens valves and lets seawater rush into large ballast tanks inside the hull. This makes the submarine heavier on average than the surrounding water, so it sinks down into the depths, just like the flat steel sheet from earlier, but on purpose and under full control. When the crew wants the submarine to rise back up to the surface, they use powerful blasts of compressed air to force all that seawater back out of the tanks. The submarine becomes lighter on average again, lighter than the surrounding water, and it rises smoothly back up to the surface. This is how submarines can dive to incredible depths and then return to the surface whenever needed, all using the exact same simple idea Archimedes noticed in his bathtub over 2,000 years ago. Regular ships use a smaller, gentler version of this same idea, without ever fully sinking on purpose, of course. But the underlying idea is identical in both cases. There is actually one more layer to this that most people never think about. Ballast tanks are not just useful for going from empty to loaded. They also help a ship stay balanced from side to side, not just up and down. If a ship's cargo gets loaded unevenly, with more weight sitting on one side than the other, the ship can start leaning. Crews can pump ballast water into tanks on the lighter side to even things back out, almost like adding weight to one side of a seesaw to balance it. Without this trick, a badly loaded ship could tip dangerously even in calm water, long before it ever reaches rough seas. Engineers also use ballast water to help a ship handle storms better. A ship riding too high and too light gets tossed around by waves much more violently because there is less mass resisting the push and pull of the water. By adding ballast at the right time, crews can make a ship sit lower and ride more steadily through rough conditions, cutting down on dangerous rocking that could otherwise damage cargo or injure crew members. It sounds almost too simple to matter this much, but getting the ballast wrong has caused real accidents throughout history, which is exactly why modern crews calculate these numbers so carefully before every single voyage. Now let's look at just how far humans have pushed this idea in real life, because the numbers involved are almost hard to believe. Consider a ship called the Knock Nevis. It was an oil tanker built in 1979 at a shipyard in Japan, and to this day, it holds the record as the largest ship ever built by humans. Its hull stretched an astonishing 458 meters long. Its width was 68 meters. When it was fully loaded with cargo, the bottom of the ship sat 24 meters deep in the water. That is roughly the same as an 8-story building sitting completely underwater. This ship could carry 564,000 tons of oil at once. When you add the total weight of the ship itself, plus all that oil cargo together, the number goes past 600,000 tons. To put that into perspective, that is roughly equal to the weight of about 4 million regular cars, all combined into a single object floating on the ocean. And the entire reason it stayed afloat traces directly back to a single simple idea that a Greek man supposedly figured out while taking a bath. Another jaw-dropping example is the aircraft carrier named the Gerald R. Ford. This is currently the largest warship on the entire planet, and it entered service with the United States Navy back in 2017. It stretches 337 meters long and weighs around 100,000 tons. At any given moment, this single ship can carry about 7,000 people at once, combining sailors and aircraft crews together. It carries more than 90 aircraft and helicopters on board, along with massive amounts of jet fuel, weapons, and food supplies for everyone living aboard. Despite carrying all of that enormous weight, the Gerald R. Ford can still move through the ocean at speeds up to 30 knots, which works out to roughly 56 kilometers per hour. That is genuinely faster than plenty of small recreational speedboats, even though this ship weighs about as much as a small mountain. 2 nuclear reactors power this entire ship, spinning 4 separate propeller shafts to push it through the water at that speed. But underneath all of that incredible engineering, the exact same basic idea from a bathtub over 2,000 years ago is still the reason the whole thing floats in the first place. Everything sounds pretty amazing so far, right? A steel object the size of a small mountain, floating calmly, moving fast, staying safe. But floating is not automatically guaranteed forever. Sometimes even the most carefully designed ship in the world can lose this battle against the ocean, and when that happens, the results can be absolutely devastating. Section 5. When the math runs out. On April 14, 1912, a massive ship called the Titanic was sailing across the North Atlantic Ocean at a fast speed, moving through waters known to have floating icebergs at that particular time of year. For its era, the Titanic was considered extremely well protected against sinking. Its hull was divided into 16 separate watertight compartments, similar to the ballast tank idea from earlier, except these were designed purely for safety rather than balance. Engineers had calculated that the ship could stay afloat even if any 4 of those 16 compartments completely flooded with water at the same time. That seemed like more than enough safety margin for basically any accident they could imagine. Then, an iceberg hit the ship in a way that nobody had actually planned for. The impact happened on the right side of the ship, at a slight angle, almost like a long, glancing scrape rather than one single giant hole. Instead of punching one massive hole in one place, the collision caused a long series of smaller cracks and dents stretched along the hull, damaging 6 separate compartments all at the same time, instead of the maximum 4 the engineers had planned for. Water began pouring in slowly, but through 6 different points, all at once. The ship was suddenly facing a situation its safety design had never accounted for. As the front compartments filled with water, the front of the ship began sinking lower and lower into the ocean. Water eventually spilled over the tops of the internal dividing walls between compartments, because those walls did not reach all the way up to the top deck, only part way up. That gap let water spread from one compartment into the next one, like an ice cube tray overflowing from one section into another. Meanwhile, the back half of the ship rose higher and higher out of the water as the front sank. Eventually, the ship was tilted at such a steep angle that the steel simply could not support its own enormous weight anymore, and the entire hull snapped apart in the middle. Out of 2,224 people aboard the Titanic that night, only 720 survived. The rest could not be saved in the freezing cold ocean water. What makes this even harder to accept is that the ship's engineers were not careless or lazy. They genuinely believed they had built one of the safest ships ever created. They had done the math for the disasters they could imagine, a single big collision punching one large hole in one place. What they never planned for was a long, scraping impact that damaged several compartments at once in a pattern nobody had tested. It is a reminder that even very careful math can fail if it does not account for every possible way something could go wrong. The ocean, it turned out, was more creative than the engineers had been. This tragedy completely changed the rules for building ships all over the world. After the disaster, a new safety rule became mandatory everywhere. Watertight dividing walls inside ships now had to extend all the way up to the top deck, not stop partway up like they did on the Titanic. This single change prevents water from spilling over from one flooded compartment into the next one nearly as easily. Because of the Titanic disaster, an international safety agreement for ships was signed in 1914, and an updated version of that same agreement is still followed by ships around the world today. But the Titanic is not the only hard lesson the ocean ever taught engineers. In September of 1994, a ferry called the Estonia was sailing from Tallinn to Stockholm, carrying 853 people on board. A powerful storm hit that night, with waves reaching heights of 4 to 5 meters, crashing repeatedly against the front of the ship. At the very front of the ferry was a giant metal door called a bow visor. It sealed off the entrance used for loading vehicles onto the ship. That night, the constant pounding from the waves proved too much for it. The heavy door, weighing about 55 tons, tore completely loose from the ship and sank into the ocean. With that door gone, ocean water rushed straight into the vehicle deck within just a few minutes. This triggered something engineers call a loose water effect. Hundreds of tons of seawater began sloshing freely back and forth across the open vehicle deck as the ship rocked side to side in the storm. Every time the ship tilted even slightly to one side, That loose water rushed toward that same side, adding even more weight there and making the tilt worse than it already was. Then it would slosh back the other direction on the next roll, but by then the ship was already tilting harder and harder each time. The ship began leaning further and further to one side. The loose water kept making the lean worse with every single roll. Within about 20 minutes, the Estonia rolled completely over and sank into the ocean. Out of the 853 people aboard, only 137 survived. It remains the deadliest peacetime shipping disaster in European waters since World War II. This loose water problem is actually one of the sneakiest dangers in all of shipping because it does not need a huge amount of water to cause huge damage. A ship carrying a small amount of water sitting still and evenly spread out across a deck is not very dangerous at all. But the moment that same water is free to slide from side to side as the ship rocks, it stops behaving like a small amount of extra weight and starts behaving like an active force working against the ship's balance every single time it rolls. Engineers now design vehicle decks and cargo holds with this exact danger in mind, using dividers and drainage systems specifically meant to stop water from ever building up and sloshing freely like it did on the Estonia that night. Both of these disasters share something important in common. The basic science of floating did not fail or stop working in either case. It worked exactly the same as it always does. What actually happened is that damage, flooding, and extreme conditions pushed past the limits that each ship's design could safely handle. That is exactly why modern ship engineers now build in a huge safety cushion above what basic math says is technically needed. Today's ship hulls are designed to withstand stresses 1.5 to 2 times greater than what the ship is actually expected to face in normal real-world conditions. Building in that much extra strength costs a lot of extra money, but it is considered a necessary price to pay so that disasters like these become far less likely to ever happen again. While engineers were learning hard lessons from these tragic disasters, shipbuilders were also constantly pushing in a completely different direction at the very same time. They kept asking one big question: just how large can a ship actually get? Purely from a floating standpoint, there is almost no upper limit at all. You could theoretically build a ship a full kilometer long, and it would still float perfectly fine as long as its average packed-togetherness stayed lower than seawater's. But once you try to actually build something that huge in real life, a whole different set of problems shows up fast, and these problems have nothing to do with floating at all. The first big problem is hull strength. Out on the open ocean, a ship's hull is constantly being bent and flexed by waves. A wave lifts the front and back of the ship up at the same time, leaving the middle section hanging in open air with nothing supporting it underneath. Then that same wave passes underneath the middle of the ship, and the whole hull bends the opposite direction instead. This bending and flexing happens thousands of times during a single voyage across the ocean. At around 400 meters of length, these bending forces already become extremely serious engineering challenges. The Knock Nevis, at 458 meters long, was already operating right at the very edge of what steel hull strength could safely handle. That is part of the reason it could only travel through certain deep ocean routes and could never enter most ports around the world. It was too wide and too deep for most harbor channels, and it could not fit through either the Suez Canal or the Panama Canal. By 2010, the ship was taken apart for scrap in India because there was simply no practical use left for a ship that enormous and that limited in where it could actually travel. The second big problem is how hard giant ships are to steer and control. Even at full cruising speed, the fully loaded Knock Nevis could not turn in a circle smaller than about 3 kilometers wide. Its stopping distance, from top speed all the way down to a complete stop, stretched about 8 kilometers and took roughly 20 minutes to accomplish. Because of this, ships this massive always require small tugboats to help guide them safely in and out of harbors. The giant ship itself is physically incapable of steering precisely enough on its own to dock safely next to a pier. The bigger a ship gets, the more tugboats are needed to help it, and the more expensive each single trip into a port becomes. The third big problem is simply the infrastructure of the entire world. The largest cargo ships in operation today are massive container ships, some stretching close to 400 meters long and 61 meters wide. In 2024, a container ship called the Ever-A-Lot, built by the shipping company Evergreen, entered service. It can carry roughly 24,000 standard shipping containers at once. A standard shipping container is a steel box about 6 meters long. If you lined up all 24,000 of those containers end to end in a single row, that row would stretch 144 kilometers long, all carried by one single ship on one single voyage. However, a ship this enormous already cannot pass through most shipping canals around the world, and it cannot enter many ports that have shallow approach channels leading up to them. Even with all of these serious real-world limits, the shipbuilding industry keeps pushing toward bigger designs wherever it actually makes practical sense to do so. A company called Samsung Heavy Industries, working together with several oil and gas companies, has been developing giant floating factories designed to produce liquefied natural gas directly out at sea. These planned structures are expected to stretch somewhere between 500 and 600 meters long, with widths reaching around 100 meters. These are not simple cargo ships at all anymore. They are entire floating industrial factories, capable of pulling natural gas directly up from the seafloor, cooling and processing it right there on board, and then transferring the finished product onto separate tanker ships. These massive floating plants can stay anchored in the exact same ocean location for years at a time, without ever needing to enter a traditional port at all. The very first structure of this kind, named the Prelude, was built by the energy company Shell off the coast of Australia, and it began operating back in 2018. It stretches 488 meters long and 74 meters wide, and its total weight when fully loaded goes past 600,000 tons, putting it right in the same weight class as the legendary Knock Nevis. But its actual job is completely different. Instead of simply transporting a product from one place to another, the Prelude produces that product directly at its location, out in the middle of the ocean. So here is the real answer to the big question about size limits. The basic science of floating would honestly allow humans to build ships far larger than anything that exists today. What actually limits ship size in the real world has almost nothing to do with floating at all. It comes down to port infrastructure, the physical strength limits of steel, and whether building something that huge even makes financial sense. Right now, there simply is not a strong enough reason to build ships longer than about 500 meters. There would be nowhere sensible to dock them, and no efficient way to move that much cargo to where it actually needs to go. So let's bring this all together. A massive steel ship does not float because the steel somehow magically becomes lighter than water. It absolutely does not. Steel remains roughly 8 times heavier than water, no matter how large or small the ship is. A ship floats because of its shape, a giant hollow structure that traps an enormous volume of air and empty space inside its steel walls. When you average out the weight of all that steel together with all of that trapped air, the whole combined package ends up lighter on average than the same amount of ocean water. The water pushes back up against the ship with a force exactly equal to the weight of the water it displaces out of the way. That single rule was discovered by a man named Archimedes, sitting in a bathtub more than 2,000 years ago. The basic idea has never changed since then. Only the size of the ships and the precision of the engineering behind them has changed. Humans took one incredibly simple idea from nature and built an entire worldwide system of trade and shipping around it. Today, roughly 90% of everything traded around the entire world travels by ship at some point. Your phone, your shoes, the fuel in your car. At some point, almost all of it sat inside the hull of a massive steel ship, floating calmly on the ocean, thanks to nothing more than water pushing back against the space that ship took up. If you liked learning how something this massive can float, using nothing but a simple idea from a bathtub, make sure to like this video, subscribe to the channel, and turn on notifications so you never miss the next one. We cover stories just like this one all the time, where a simple rule of nature turns out to be hiding behind something huge and unbelievable. Before you go, here is a question for you. If you had to guess, what do you think is the heaviest object humans have ever managed to make float on water? Drop your guess in the comments below, and if you enjoyed this one, check out our other videos where we break down more incredible feats of engineering hiding in plain sight.